Okay, so here's what we were talking about last time. This idea that we can write the stretching factor in a change of variables formula as a fraction. And well, we've already written it like a fraction, but now we see another sort of justification for it because its reciprocal is written like you would expect if you treat it like a fraction, right? So the argument was that this is the stretching factor when you view x and y as a function of u and v. That's just again how you write that determinant. If you view u and v as functions of x and y, this is how you would write the stretching factor. From this algebra, they should be reciprocals of each other, and they are. Okay, all right. So now I claim that's a really useful observation. So here's why. Let's consider this example. I want to compute that integral. The integral is defined on this little domain in here that's squeezed in between these four curves, and we talked about those four curves last time. So here they are. So we have such an odd little shape there. Don't want to have to do an integral over this odd little shape. You can just imagine what a nightmare that would be, right? I mean, you're going to be slicing through that corner and then also through that corner, thus giving you three integrals. Or going the other way, again, it's going to be three integrals. So, nasty domain. All right, now, in order to do this, notice that what I need to be able to rewrite dx dy. Here's how I write dx dy in terms of du dv. In other words, if I want to do a pullback to the uv plane. So specifically then, I'm going to need to compute partial xy, partial uv. That's the stretching factor I want. Okay. Which, by the way, if I were to go straight at it and directly compute this thing, notice I would need to know x and y as functions of u and v. Okay, and it turns out that in this situation, finding x and y as functions of u and v in such a way as to make the change of variables easy to motivate is not particularly convenient. So what we're going to do is go backwards. We're going to write this whole problem backwards effectively. I'm going to view u and v as being functions of x and y. And the motivation for these functions is really straightforward. Look at these first two equations that I'm given. These first two equations, that's for this curve and that curve, xy figures very prominently in those equations, right? So why don't I just call that u? Right? And now similarly, in these two equations, those are the equations for the, oh, come on, do better than that, these two curves here. Right? Notice that xy squared figures very prominently in those equations, and so why don't I just call that v? Seems like a reasonable thing to try anyway, and it's going to turn out really nice. Bear with me. So having made these choices, u equals xy, v equals xy squared, let's rewrite these curves. So this curve here, for example, that curve has equation xy is equal to 6, which, in light of this, I can rewrite as u equals 6. And u equals 6 in the uv plane is a straight line. Everybody see what happened there? So, a good trick to remember for the future, by the way, and we have a lot of details still to work out, but if you are given your domain in the form of a bunch of equations that where there are two expressions involving x and y that figure very prominently like this, notice that you, just by calling them u and v, like we did here, you can turn those curves into straight lines, which everybody likes. Okay, so continuing, this curve here, xy is equal to 10. That curve, with that in mind, becomes u equals 10. That's that straight line. Similarly, this curve, xy squared equals 7, becomes v equals 7. And this curve, xy squared equals 5, again with that in mind, becomes that straight line. So this new function that I've defined here called h, that function motivated as I suggested, has the nice feature that it relates this really undesirable domain that we're stuck with to a rectangle. It's everybody's first choice for a domain for a double integral. Okay. All right. But big problem. Notice the arrow's going the wrong way, right? We're accustomed to pulling back. This would suggest we're going to push through or something. Right? It's not clear how that works. Well, you could argue that, look, just solve for x and y in terms of u and v. It's just a little bit of algebra, right? You could do that. And certainly in this case you could. Let's not, though. I want to show you how it's not necessary to do that. It's certainly more convenient to do it this other way that I'm about to show you. So even though you could solve for x and y in terms of u and v and do it just like we did on Friday, check out the alternative. Keep in mind, we've already agreed that we need to rewrite dx dy in terms of du dv. Therefore, this is what I really want to know: partial xy, partial uv. That's what I want to know, for which I would typically need to solve for x and y, which I just said I don't want to do. So, but notice that I can solve for it simply by understanding u and v as functions of x and y, computing that Jacobian determinant, and taking a reciprocal. Right? So that's what I'm going to do here. I've got this nice set of formulas for u and v in terms of x and y. Makes for a really easy calculation here. Right? A couple partial derivatives, take a quick determinant, boom. There's that partial. And then the thing that I wanted, it's just a reciprocal of that, 1 over xy squared. Very handy dandy. Everybody on board? All right. Okay, so now proceeding along, there is this awkwardness of how am I going to rewrite these things. I've got this x here. How am I going to rewrite that in terms of u and v? In previous examples, the way you rewrote x in terms of u and v is you just looked at your change of variables function. Here's the last example we did on Friday. X was given as a function of u and v. That's what the change of variables function does. Right? So it used to be a triviality. Now we don't have that in this example. Kind of in some sense the whole point of this exercise is to talk about what do you do when you don't want to view x and y as functions of u and v. Right? So problem, right? How am I going to rewrite that x squared, that x, or more to the point, how am I going to rewrite x squared y cubed in terms of u and v? And then there's this further problem, this stretching factor. How do I rewrite that in terms of u and v? And well, it's a problem, right? The first observation I want to make is don't try to do these separately, because technically you don't need to. Right? Technically, all you need to do is to rewrite this product in terms of u and v. Right? So that's technically easier. It's one thing instead of two, and also it's, it's an easier problem because it avoids having, this arbitrary partition in what you're trying to compute. So this is really only one thing, xy, that I need to rewrite in terms of u and v. Now let's look at our formula here, and how am I going to rewrite xy in terms of u and v? Oh, well, we got lucky. Right? So, how nice. You won't always get that lucky, but in this case, it turns out really convenient. That xy is just v. Right? And it's all downhill from there, yeah. Oh, did I write it wrong? Oh my gosh. Wow. How did I get that wrong? Well, you know what? That's funny is you're the first person who's noticed this particular typo in my notes. And I've been using these notes for a couple of years now. So, you're quite right. Okay, so xy is what we're interested in. That's u. So xy equals u. This should be a u here. So please make that change in the notes if you have them printed out or if you have them in a format that you can comment on. Thank you for the catch. Yeah. Okay. Anybody else? By the way, the bounds are a freebie. again, so we've converted our integral now over to here. This is our new domain. And so the bounds are, well, clearly u goes from 6 to 10, and v goes from 5 to 7. And thus, that. Okay, all right, now, so you complain, what if we didn't get lucky, right? This was super lucky. What are the odds? Surely we can't expect to just always get lucky in real life, right? So what do? Well, you do have a little bit of an algebraic problem there, and it's something you have to kind of tinker with. Now, the method is going to be situation specific. There is no single sort of algebraic hopper that you can throw a question into and turn the crank 3 times and out comes the answer, right? So here's what I would have tried if I hadn't gotten lucky like this. I would have observed that, okay, the expression that I'm trying to simplify is a product of powers of x and y. Now this is just a structural observation. This thing that I need to rewrite in terms of u and v is a product of powers of x and y. U is a product of powers of x and y, and v, oh, did I just get this backwards? I'm confused again. U is, yeah, okay, right. V is xy squared. So I'm interested in a product of powers of x and y. I want to rewrite that in terms of a product of powers of x and y. And so it seems like a reasonable thing to try to turn a couple of products of powers of x and y and turn that into another product of powers of x and y. Is how about we raise them to powers and multiply them? Seems like a reasonable guess, right? I'm probably not just going to be adding, right? It's hard to figure out how a sum of these is going to turn into that, what I have highlighted in yellow. So this is pure algebraic sort of intuition and speculation. Everybody see what I'm saying? This is not an algebraic hopper. Seems like a reasonable thing to try. And then now having made this speculation, you turn this into that, and thus the unknown a and b relate to these powers m and n like this. And then you can solve for what you need. Okay, so anyway, that's what you would do in that situation, and then kind of morally rip this off for other situations that you might encounter. Okay. So what about in 3 dimensions? Right? All the change of variables we've done so far have been in 2 dimensions. R3 is same deal, right? You could imagine having a domain like this. What a nightmare of a domain that would be, right? Imagine slicing that up with plain slices and ugh. Right? I can't even count how many pieces I would have to do separate triple integrals on. The counting of that would be a hard geometry problem, right? Much less doing the integrals. So same idea. If you can view that as being the image of something nicer, for example, a rectangular box, then you can talk about doing a pullback, right? X, Y, and Z are functions of u and v by way of whatever that g function is. The only remaining question is the stretching factor, right? dx, volume in the xy plane comes from volume in the uvw space. From volume in the uvw space gets stretched out by some factor. What is the stretching factor? Again, we're not going to derive this at this stage of the course. We'll talk about that a little bit later on. For right now, I just want to assert that this is it. And you'll notice it's, again, the Jacobian determinant. Not terribly surprising, I suppose. Exactly the same formula. 3 variables instead of 2, so it's a determinant of a 3 by 3 matrix instead of a 2 by 2 matrix, but it's pretty much the same formula. Again, notice the notational convenience here, which is convenient because then this equaling that can be viewed, and again, that doesn't technically make sense, but notationally it's highly suggestive, and it's always going to line you up in the correct direction. Okay. All right. Okay, quick example. Suppose you have this as your change of variables function. Notice x, y, and z are functions of u and v and w. Right? Now, by the way, what does this function look like? Whoa, hey, that's going to be a hard draw. Let's not worry about that. Let's just sort of take an algebraic point of view on this example. Anyway, x, y, and z are functions of u, v, and w. You can compute those partials. Take that determinant, right, to get the stretching factor. A little bit of algebra there. You get this. So this is the stretching factor that you associate with that change of variables function. Is everybody on board so far? Okay. Suppose you're looking at the image of this box in the UVW space. The image is some contorted, twisted, highly undesirable domain, but if I can pull it back to an integral over this box, well, the box is an easy domain, right? So, for example, let's consider this integral right here. Doing the pullback, right? Z comes straight from the change of variables function. Z is w squared minus u. Let's come back up here and see where I got that. Z is w squared minus u. Right. Our change of variables function, our change of variables stretching factor, Jacobian determinant. Right. Notice I've got to go in the correct direction. We already computed this Jacobian determinant. It's 8UVW minus 1. Now, whoa, hey, slow down. Where do those absolute values go? It's supposed to be the absolute value of that. I claim that I know that this is positive. Let's think about it. How do I know that 8UVW minus 1 is positive? Well, you've got to look specifically at what do you know about U, V, and W. And you can see what we know about U, V, and W right here. Right? U is at least 1, V is at least 2, W is at least 4. That means that UVW is at least 8. Right? This is at least 8, which means that's at least 64, which means that that is at least 63, or more to the point, not negative. Everybody happy? Okay. So I can lose the absolute values. And now I have an easy triple integral. It's just a polynomial, so crank. Okay, so I want to show you a point of view on symmetry. We've already talked about symmetry. This is not a new symmetry tool, but I just want to give you a point of view on why that symmetry result works that we talked about a long time ago. And that is to think of the reflections that we were using in those symmetry arguments. Let's think of them as change of variables functions. Right? Just bear with me here. Doesn't seem like doing a reflection would be useful as a change of variables. The whole point of a change of variables is to significantly change the shape of the domain so that the domain becomes an easier shape, and reflecting, I feel like it's going to really do that. But something really nice turns out. First, an observation. This is just a geometric appeal, but a reflection has no stretch in it. Right? Nothing gets bigger by way of a reflection or smaller. So let's consider our scenario where we have a symmetric domain with an odd function, and let's see what we can conclude. First of all, because the domain is symmetric, the domain is its own reflection. There's where we use the symmetry. Okay. Now, next step in the calculation, I'm going to observe that this is a pullback. So bear with me. We're doing an integral over an image of a domain. We pull back to the pre-image. Right? That's what change of variables is. Notice everything else goes through, and let's see. Oh, that stretching factor. Stretching factor in a reflection is 1. So that goes away. Now, next thing, notice our function is odd. Thus the minus sign here. Right? And so what we have then is that the integral we're interested in is a negative of itself and therefore 0. So that's a quick argument for proving that symmetry result. Anyway, I just like to show students that. I think it's kind of cool. Similarly for triple integrals, I did it for double integrals here, but exact same argument. Yeah. Oh, I'm sorry. Was that a no? Okay. Yeah. Okay. Anybody else? Feel free. Okay. So recall in this chapter, chapter 14, we're going to do a lot of bouncing around between topics. The order that the book does it is fine. I just prefer to do things in a different order. So by doing change of variables, that's from near the very end of chapter 14, I claim that we have some nice tools at our disposal to do some of the subjects that were covered before. So specifically integrals in different coordinate systems. So our next calculus topic is going to be how to do integrals in different coordinate systems. Like, what does it mean to do an integral in polar coordinates? What does it mean to do an integral in spherical coordinates? Right? In order to do that, I have to first make sure that everyone's strong on what are polar coordinates and what are spherical coordinates, etc. So that'll be the rest of today, talking about coordinate systems. So y'all know the rectangular coordinate system. This is the good old, plain old XY coordinate system in R2, for example, XYZ in R3. It's exactly sort of what you think. And there's something really nice about rectangular coordinates that is something we perhaps take for granted because it's perfectly obvious and so it's beyond convenient. It's we almost rely on it when we're doing rectangular coordinates, but that is rectangular coordinates are unique. So if you give me any point in R2, right, not only does it have coordinates x and y, but there is exactly one way to write coordinates x and y that describe that point in R2. All right, so that's not true in polar coordinates. The first sort of lead-off thought that I want to have about polar. Don't think of polar coordinates as somehow being uniquely determined by a point. It's not. It goes the other way. If you give me coordinates, then yeah, that defines a point in R2. But any single point in R2 actually has lots of different pairs of polar coordinates. So anyway, that's sort of an awkward thing. Now, I think most of you all have seen polar coordinates, at least some. Curiosity, show of hands, how many people have at least some vague experience with polar coordinates? Most. Okay, great. So anyway, very quickly, the idea is that there's two numbers, r and theta. Theta defines what I'm going to call a direction. Right, so it's the measurement of this angle here, and to be specific, it's that angle measured from the positive part of the x-axis and measured going counterclockwise. Always counterclockwise. That's the rule. Arbitrary, but fits. Okay. So with that direction having been defined, r then says how far do you go in that direction, with the understanding that if r is negative, just go backwards. Right, so theta defines a direction. R, you can almost think of theta as defining what I'm going to loosely call an r-axis. It's not really, right? But it's as if there's an r-axis, and then r tells you a coordinate along that axis. So negative on the other side and positive on the forward side. Okay. So that's the idea, and you'll notice that for any r and theta, you can follow those directions. And that gets you to a well-defined location in the xy plane. Okay. Here's the formula. It's not hard to persuade yourself of this formula. It involves looking at this triangle. Right? And you know this angle, theta, and you know this distance, r. And x is r cosine theta, y is r sine theta. So flashback to trig. I hope everybody's comfortable with that right there. Everybody happy? Okay. Yeah. So one way you can think of this, and this is just in case it might be useful, you can think of this as kind of taking the r theta plane and distorting it in the following way. It's like we're going to take this segment here, and that's part of the r axis. That's where theta is equal to 0, you'll notice, and r is positive. And so that actually goes over to there. And then let's look at what about, that. This is, well, okay, so this blue line I've drawn here. It's a bunch of points that all have the same value of theta, but it's a larger value of theta. Theta is increased a little bit. And so that ends up being like that. Right, and you can sort of keep going. This is that. And this is that. So one way you can think about this is, how I think about it sometimes. It's like the entire theta axis. Notice theta axis is where r is equal to 0. It's like all of that's getting pinched down to a point down there. Right? And then these colored lines kind of fan out like that. Oh, anyway, this is a point of view. Okay. So let's explicitly see some of the non-uniqueness of polar coordinates. So you think about this point here, for example, and you might comfortably think of that point as being defined by, well, you look, there's an angle and there's a distance, and maybe that gives you that point right there, and you might feel pretty satisfied. Well, come on, those are the polar coordinates of that point. But here's the thing. Notice that if you were to go an extra 2 pi in the theta direction, same point. Different polar coordinates, same r, different theta, gets you to the same point in the xy plane. And arguably a little weirder, if you go, let's see here, okay, so from these polar coordinates that get you to that point, if you go up just pi, right, not 2 pi, just pi, of course that only takes you halfway around, but it takes you halfway around to a point where if you then go negative r in that direction, so that direction there, and you go backwards by a distance r, well, that gets you to the same point. Okay. So there's infinitely many pairs of polar coordinates for a given point, and infinitely many in there's kind of to infinity, right? It's like there's infinitely many of these, and there's also infinitely many of these, sort of on the other side. So, weird. Okay. Be careful how you write these down. There's some ambiguities. So for example, if you just kind of carelessly write down, 1 comma pi over 6. What does that mean? Right? If you were to just, before there was any mention of polar coordinates, if you write down, a comma b, the understanding is that, well, the first coordinate is x and the second coordinate is y, and that's the convention, right? When you write down 1 comma pi over 6, it's not entirely clear what you mean. Now, you may look at this and think, well, that looks like an angle, so that must be theta. So this must be an r comma theta, right? So this is the point where r is 1 and theta is pi over 6, aka this must mean this point, root 3 over 2 comma 1/2. And maybe that's what the writer meant, but it doesn't have to be. I mean, just because that pi over 6 kind of looks like an angle, right, that doesn't necessarily mean that it is. There is a point where x is 1 and y is pi over 6. That's a thing. That's a real location, right? So, got to be clear, right? So, if you write this down, if you were thinking this, put some sort of a denotation, like r comma theta equals 1 comma pi over 6, right? Or you could say polar coordinates 1 comma pi over 6. Remove the ambiguity. Okay. All right. Is everybody on board with this? Any questions? Okay. So we have these formulas up here for converting from polar coordinates to rectangular coordinates. If you give me an r and a theta, plug in, bam, there's your x and y. Now let's talk about how to go the other direction. Right? Okay. A lot of you have seen formulas along these lines. So, for example, now I'm going to write down temporarily here, and then I'm going to scratch them out. What you may have seen in other contexts, and this is a little too sloppy and careless. It's not quite true. A lot of people would rather go ahead and just directly solve for the r. And say, look, r is square root of x squared plus y squared. And likewise, theta is arctan of y over x. You might have seen both of these written down. So let me complain now. You just can't know that these are true, right? This formula here is saying that all r's in polar coordinates must be positive. That's what that says. It's not true, right? I mean, we talked about, what do you do if you have negative values of r? Well, you go sort of, backwards along that axis. So it's just not true, right? Likewise, this right here suggests that all polar angles must be between negative pi over 2 and pi over 2. Nope, right? This is not true. But this function here, arctan, very specifically only takes those certain special values. Right? So neither of these formulas is true reliably. Now they may be true often, and they may be true most of the time in situations that you might be likely to encounter, right? But that's otherwise known as false. Yeah? Okay. All right, so do be careful about that. Another thing to be careful about is don't play too fast and loose with the options. So let's look at this point here. X equals -1, y equals -1, and not hard to persuade yourself that r has got to be one of those two values, and theta has got to be, well, I mean, it could be pi over 4. It could be pi over 4 plus any multiple of 2 pi, but it also could be 5 pi over 4 plus any multiple of 2 pi. Right? So a bunch of different options there. That just comes out of taking arctan. By the way, in case I haven't already made this point a million times, I think I have, make sure you're really good at trig. Right? Make sure you remember values of sine and cosine at the standard angles. Make sure that you can, for example, look at tan theta equals some value and think through, for standard angles, what are my angle options, right? Because it just doesn't go away. All right, so the point I want to make here is don't be too careless in terms of how you group these up. It is true that r has got to be one or the other of these two values. It is true that theta has got to be one or the other of these two values, but it's not true to say that these are your options. That's wrong. It's not hard to see why. Let's look at this alleged point. R is square root of 2, theta is pi over 4. That's over here. That's not the point we're looking at, right? If theta is 5 pi over 4, that defines that direction. But if we go -2 in that direction, it gets us to here again, right? So both of these, this pairing that I just kind of arbitrarily made, gets us to the wrong location. So heads up on that. Don't just assume that it's going to be, well, your favorite of the two options that these formulas up here give you. Yeah. Okay. All right. So in this case, they pair like this. Right? That's that, you might say. And then this, come on, I want to change colors there. This gets you to the same point by going backwards. Okay. All right. So, okay. What do equations look like in polar coordinates? Here's some easy ones. If r is equal to 3, well, circle, right? Pretty easy one. What if theta is a fixed value? Okay, well, again, it's pretty straightforward, right? All the different points that you can get to by pointing in only one direction. That's a line through the origin, right? Okay. Sometimes you got to just plot some points, and you get these weird shaped curves that have French names that I have forgotten since the day after the test in my high school geometry class, right? But you got to plot some points. By the way, I found another typo in the notes here. These are supposed to be over 2. Sorry about that. I was being too quick when I wrote this down. So yeah, let's go through and plot some points. So r equals sine 2 theta. Well, when theta is 0, r is 0. Okay, then when theta is pi over 8, okay, well then I'm taking sine of pi over 4, and that gives me r is square root of 2 over 2. Right, etc. Go through, plot the points, and your points, it ends up that the curve kind of ends up doing something kind of like this. Makes a 4-leaf clover that coincidentally I drew in green. So anyway, it's kind of weird, but that's what you get. Here's another one. 1 plus. And I'll let you guys go through and check out the points, right? But as you go through, what you find is, and again, I forgot my over 2's. Sorry about that. And it makes this shape that does something kind of like that. Okay. All right. What if you want to convert one way or the other? This r equals 3. What's the rectangular equation from that of that thing? And of course, we know algebra 2 tells us circle of radius 3 centered at the origin. We already know the answer. But notice that you could take this equation, square both sides, and having squared both sides, take advantage of the fact that we know that r squared is x squared plus y squared. Now we've algebraically derived this equation from that, the rectangular equation from that polar equation. Okay, so games like this. Here's one. How do you get from theta equals pi over 3 to the equation of that line in rectangular coordinates? Well, take the tangent of both sides. Tangent y over x. There you go. That's the clever little algebraic trickery. The way you learn how to do these is you see a certain number of usages of these tricks, and then you mimic. Right? So these are those tricks. Here's another one. R equals cosine theta. What is that? Well, now there's a temptation to square both sides because you know r squared is x squared plus y squared, and that nice. But cosine squared is not something that we can easily substitute for. So instead of squaring both sides, multiply both sides by r. That's the slick move here. Right? And then r squared is x squared plus y squared. R cosine theta is x, and then it's just a matter of completing the square, doing a little bit of algebra 2, and there's your equation for a circle. Everybody on board? Okay. All right, now I have a hard example here. This is a hard one. Suppose you have this rectangular equation and you want to write the polar equation. How would we do this? Well, multiply everything out first. Okay, sure. X squared plus y squared is r squared. Sure. Take all this stuff, move it over to the other side of the equation, lose the minus signs. Fine. X is r cosine theta. Y is r sine theta. Right. Okay. Then I did something weird. I pulled out a factor of 4 from both of these coefficients. Not that there was a visible factor of 4, right? But by pulling out that factor of 4, what I did is I made a pair of numbers that are cosine and sine of an evident angle. Right, now, if two numbers are going to be sine and cosine of an actual angle, the sum of their squares has to be 1. Right? That certainly wasn't the case here. These numbers, the sum of their squares is 16. Right? In some sense, these two numbers here, if I wanted those to be a cosine of something and sine, if I wanted these to be thought of as representing a point somewhere, these two numbers have a magnitude of 4. So that's why I divided out the 4. You divide out this 4 so that what's left over is a pair of numbers that have magnitude 1. You can rewrite this then as, I kind of algebraically skipped a step here. You can rewrite that as 4r and then cosine theta cosine pi over 6 plus sine theta sine of pi over 6. And then recognize angle addition formula. Angle subtraction formula, actually. And that's cosine of theta minus pi over 6. Do y'all remember your angle addition formulas? Show of hands. Nope. Okay. Do y'all remember that there are something called angle addition formulas? Okay, right, good. Okay. So I'm a believer in them. Okay. I think they're very, very handy. Little situations like this come up, and kind of handy to remember angle addition formulas. So I would encourage you to look up and remember. And by the way, just for sine and cosine, I know that there's technically 6 of them, but don't worry about the angle addition formula for cosecant. Right? But sine and cosine, it's 2 formulas. They're not that hard to memorize. I suggest it. Now, for your curiosity, if you are an engineering student, and if you are going to be taking Math 216 next term when I'll be teaching it, it will be a requirement in Math 216, right? So heads up, you might as well memorize it now because you're going to have to memorize it later anyway, right? So why not get, double the benefit of that memorizing effort? So anyway, cool fact. Okay. All right, so that's polar coordinates. Let's move on. Cylindrical coordinates. This is a coordinate system in R3. So if you have, so a point in space, in the XYZ space, right? How do you write that? And of course, rectangular coordinates, sort of the standard, But you could do what a lot of people call polar coordinates in R3, which I suppose is okay. It's more syllables. I'm not sure where you'd want to say polar coordinates in R3. I mean, you can just say cylindrical coordinates. It's easier to say. Anyway, here's the idea. If you have a point in R3, and you want to define what are that point's cylindrical coordinates, what you do is you drop a perpendicular down there in the XY plane. Right? You look at this point down there in the XY plane. Notice that that point in the XY plane has r and theta. Right? And then the rectangular z is the third cylindrical coordinate. So r theta z. And you can see why they call it polar coordinates in R3. It's because 2 of the 3 coordinates are polar coordinates. Right? So it behaves a lot like polar coordinates. The conversion formulas, the conversion formulas are the exact same as the conversion formulas for polar coordinates. We don't need a conversion formula on z. Z is z. Right? So it's very polar-like. I'm not going to spend a lot of time talking about cylindrical coordinates. There's just not that much to say. It's just like polar coordinates in the xy direction, and then z in the z direction. Right? It's whatever. Okay. So this equation here, r equals 1. Notice that gives you a cylinder. That's the name, cylindrical coordinates, right? So a constant value of one of the variables there gives you a cylinder. So cylindrical coordinates. Okay. The equation of a sphere. Not surprisingly, x squared plus y squared is still r squared. And so this equation for a sphere from rectangular coordinates gives you this equation for that same sphere in cylindrical coordinates. Yeah.
So if you have an r, you can apply the same argument of rotation around the z, the rotational symmetry around the z-axis.
For argument about what? I see what you're saying. So if you have an equation that's in cylindrical coordinates and there's no thetas in it. Yeah, totally. Absolutely. Okay, so here's the more interesting coordinate system in R3. This is harder to talk about, and I guess I can, look at that, I can fit it in. Okay, so spherical coordinates. Now this one is also sometimes called polar coordinates in R3. I think it's a big mistake. I don't encourage that at all. This is significantly different. It's significantly less like polar coordinates than cylindrical coordinates is. If you're going to have a polar coordinates in R3, it really ought to be cylindrical coordinates. Right? So this is a totally different thing. It does have one coordinate in common, but it's more different than similar. Okay. So these spherical coordinates are called rho, phi, and theta. When I wrote this down, I had just a momentary lapse of awareness, and I helpfully wrote down here just that this is the Greek letter rho. And then for some reason in my mind, I've done a lot of math and physics stuff in my class, and I just read this and I'm like, phi. I thought that was very helpful. So this is phi like that. And, of course, you all know theta. Okay. By the way, do be careful. Make sure that your phi, which has a vertical line through it, and your theta, which has a horizontal line through it, don't end up kind of blurring, right? It's real easy to kind of, to like make your phis kind of start to have a little bit of an angle to them, and then, I don't know, what's that? Right? That could go either way. That's either a sort of a theta leaning to its left or a phi leaning to its right. Right? So, anyway, another little cultural observation. I'm going to do these coordinates the way the book has done it. This is the way most math books, in my experience, have done it. Right? And awkwardly, in a lot of physics contexts, they switch which one is phi and which one is theta. And it's just enough to drive you crazy. Right? So anyway, heads up, be aware of that. I can't change that. That's out there. Right? So as engineers, I'm not sure what the conventions are going to be. You might be seeing they might call this theta, and they might call this phi in some contexts. So anyway, keep on the lookout for that. Okay. Okay. So anyway, here's the picture. These two coordinates here, phi and theta, define an angle. Define a direction as follows. Theta is this angle. It's the usual theta that defines this plane hinged on the z-axis, right? And then phi is that angle that measures how far down from the positive direction of the z-axis, how far down within that theta plane do you go to get to the direction that it wants to define. All right? Okay. All right. And then just like with polar coordinates, once you have a direction defined, then rho tells you, how far to go in that direction. Again, rho can be negative, in which case you just go backwards along the same direction. Okay, so formulas. Well, we have a trig exercise here, right? You can look at this triangle, and then notice that there's also this triangle, and play some trig games to persuade yourself what these formulas are. And here's what you get. Now, everyone should go through and do those trig games on your own. Here's the important observation to remember, and that is that this distance there, that r, is rho sine phi, and you can see that very easily from looking at this triangle. Right, that r is rho sine phi because that angle phi is the same as this angle. And rho is the hypotenuse. Rho is the hypotenuse. So, easy little trig game. So, once you remember that r is rho sine phi, notice that all this says is x equals r cosine theta. Right? And this says y equals r sine theta. So, we're 2/3 done, and we're just basic. We've made one trigonometric observation, and then we remembered these old formulas for x and y from polar coordinates. Okay, so that's very handy. And then looking at this same triangle again, right, and noticing that z is that. Not hard to persuade yourself at this one. Okay, all Also, not hard to persuade yourself, rho squared is x squared plus y squared plus z squared. Okay. All right, and I'm out of time. So we will pick up here on Wednesday. Y'all have a good day.